Okay, so we're still working on section 7.6. We're talking about inverse trig functions. At this point, we've met, I think, 3 of them. We've met the inverse of sine and the inverse of cosine. Don't want to spend too much time talking about these today, since we've already seen them. And then, well, one of the big things that you need to remember from the section is actually back here. And that's the new derivative rules that we get for our new functions, arc sine and arc cosine, or sine inverse and cosine inverse. So these new rules need to be added to your memory bank of derivative rules, and you'll also need the corresponding integral rule. This one is going to come up a lot as we work through chapter 8 in a few weeks, or maybe even next week. So that was on Monday, and then yesterday, well, we did some examples and then talked about a tangent inverse. So the thing to remember about tangent is that it has this repeating pattern of vertical asymptotes at minus pi over 2, and then this repeats with a period of pi. So if you go another pi to the right to 3 pi over 2, you would see this pattern repeating. And this just continues in both directions. So in order to get an inverse for tangent, we had to slice the domain to just between one of these segments. And the usual choice is this one, just to pick the one near the origin, from minus pi over 2 to positive pi over 2. And then to get the inverse, we think about mirroring this graph across the line y equals x that I'm gesturing at with my pen here. And when you mirror it across that line, when you exchange y and x to get the inverse function, you get the mirror image like this that has horizontal asymptotes at infinity and minus infinity. So this one is going to be pi over 2 at infinity, and then at minus infinity, it'll be minus pi over 2. And that corresponds to these two vertical asymptotes for the original function. Then we also learned the derivative of inverse tangent last time. So there was another rule to learn. And this particular derivative doesn't have any square roots in it. So it looks a little bit different than the derivatives of arc sine and arc cosine. And then we had a corresponding integral rule. Do you guys have any questions over this stuff, the stuff that we learned on Monday and Tuesday, before we move on? Okay. Well, if you do think of any questions, you know to just ask them when you think of them. So the next thing we're going to do is to walk through secant and finding the inverse of secant, or at least thinking about the inverse function arcsecant. And just like we did for sine, cosine, and tangent, what I want to do is head over to a graphing tool. Let's see, get that homework question out of the way. Okay, so head on over to the graphing tool to look at the graph of secant. This one is probably a little less familiar to you guys than sine and cosine and tangent. This one has a repeating pattern of what look a little bit like parabolas, but they're not exactly parabolas because they actually have vertical asymptotes if you look closely. So this actually blows up to positive infinity in these two areas, and this blows down to negative infinity. And maybe you can tell where those are, but I'll put in some dashed lines so that we can see them. They're at pi over 2, and then you can add multiples of pi to get to the next one. Let's see, make that dashed. Then maybe add another one at minus pi over 2 over there. And then maybe the next one further to the right, that would be 3 pi over 2 if you add 1 pi to pi over 2. Okay, so this gives us an idea of what secant looks like. But you can see that if I draw a horizontal line through this graph, we're going to get more than one intercept. So if I put my horizontal line up here, we can see it's going to intersect the graph of secant multiple times. And if I want to talk about an inverse function, we can only cross the graph once. So this means I'm going to have to restrict the domain of my secant function. Let's put in some sliders. So what I need to do, if you can see here, if I draw a horizontal line just across this one single segment, we can see that it's going to cross twice. So that means I can only include half of this parabola-like shape here. So let me move my left slider up to 0 so that we can cut this shape in half. Okay. So now I have half of this parabola-like thing, and I'm only going to intersect this one a single time. And that means I also need to get rid of all of these other ones, so I need to move my B slider in far enough to get rid of those other curves that have vertical asymptotes that go to infinity. And then I'm going to run into the same kind of problem on the bottom with this part that goes down to minus infinity. If I move my horizontal line down there, I'm going to cross it more than once unless I move my domain to where it cuts this in half as well. And maybe you can see, it's a little hard to see the exact value, of course, but you can kind of get an idea that this is about, oh, I don't know, 3.14, continuing on, otherwise known as pi. Okay. So if I make this choice for my domain, if I go from 0 up to pi, and let's get rid of some of these extra things. Okay, so if I make this choice for secant, then wherever I put my horizontal line, I'm only going to cross the graph once. Okay. So now we have a one-to-one function, which means it has an inverse. Let's go ahead and graph that in. Arc secant. Let's get a different color for it for contrast. Get rid of that line. and then maybe put in y equals x so that we can see the symmetry. Okay, so the original curve secant is in red, the one that we chopped into pieces, and the inverse function is in black, arcsecant. And it's the same as the red curve, but it's been mirrored across the line y equals x, because we interchange the role of the x and the y values to get the inverse function. So what we can do is maybe go back to the paper and write in some of those details. Okay. Before I get rid of this graph, does anyone have questions? Okay. So now you can see my paper a little bit better. So let's sketch in what we did for secant. Remember, we picked the domain to be 0 up to pi. And then the range is going to be, if you remember from the graph, well, it's a little odd. It's minus infinity up to 1. But then there was a gap up to minus 1. There was a gap from minus 1 up to positive 1, and then it went up to infinity again. And the graph looks something like this. There's a vertical asymptote here at pi over 2, and then another vertical asymptote going down this way. And then this gets mirrored across the line y equals x, and we end up with a shape like this. Let's see, so there's a horizontal asymptote that we should sketch in at pi over 2. That corresponds to the vertical asymptote here. And then this goes up to positive infinity, just like this one went to, or as this one goes to positive infinity, it goes to pi over 2, which corresponds to this vertical asymptote. And then we get the horizontal asymptote here. Which corresponds to this curve going down to minus infinity. So the domain of our secant inverse, or arcsecant, corresponds to the range of secant. So we can plug in anything from minus infinity up to minus 1, but then there's this gap from minus 1 up to 1, and then we can continue on. And then the range is from 0 to pi. Okay, any questions over these details of secant and arcsecant, and then their corresponding domains and ranges? Okay, so if there aren't any questions, I want to go ahead and move on to the derivative of arcsecant, so finding the slope of this new curve. And instead of working through the details like we did for sine and tangent, I'm just going to tell you what the derivative is. It looks a little bit like the derivatives for sine and cosine, or arcsine and arccosine, but there's this extra bit in the front. It's an absolute value of your variable. And instead of having 1 minus x squared, that order gets reversed. So we're going to have u squared minus 1 in the denominator. And then a 1 up top. And since I'm writing it this way with a u in it instead of x, I have to include the inner derivative, du dx. And in order to make sure we stay in the domain of arc secant, so we need to stay at least as big as 1 or as big in the negative direction as -1, I need to insist that the absolute value of u is always greater than 1. So otherwise, we would be trying to, if we had an actual 1 down here, we would be dividing by 0. That's why it's not a less than, excuse me, it's not a greater than or equal to sign. It's a strict greater than. If you wanted to figure out this derivative for yourself, you would have to do something like what we did last time. So you would say f of x is equal to the function secant, and then your inverse is, of course, arcsecant. And then you would use the formula for the derivative of the inverse. Let's see. So remember, this was 1 over, and then you plug the inverse function into the derivative of the original function. Okay, so this is what we worked out last time for tangent, and then the time before for sine. But I wanted to skip that particular step for today. Okay, so here's the derivative rule. And anytime you have a derivative rule, there's a corresponding integral rule that you can get just by reversing. Okay. And here it is. Here's the new integral rule. So if I take the integral of u over the square root of u squared, and then minus a squared, I'm adding in an extra constant here, and then we get a du on top. This is equal to an arcsecant. But since I added in this extra constant, we have to divide by a in the front. And we also have to divide by a inside of the arcsecant function. So this is the integral rule. And there's a few details here that we need to discuss a little bit. So you'll notice in the derivative, there's an absolute value down here in the denominator. And in the integral, the location of that absolute value has been changed up a little bit. In the integral itself, there's not an absolute value, but there is an absolute value on the right side in the actual result of your integral. So keep that in mind, where that absolute value goes. And also, you need to make sure that your constant here is actually going to be positive, and that your function u is always greater than whatever goes here. And this corresponds to the gap in arcsecant. So we have to make sure our u is always outside of this gap in the middle. Okay, so like I said, if you wanted to work out how this rule, how it really works, the details, you could use this. And then if you wanted to figure out how this works, you could try to do a U substitution in that rule and work out how A plays a role. But those are kind of technical details that we don't want to worry about. Let's see. The kind of technical details that you guys don't have to worry about. You guys should focus more on trying to use the properties in order to solve problems and leave the deriving of formulas for, oh, well, that's for me or your textbook author to deal with right now. So what we need to do is practice with these new rules. So I want to take the derivative of the arcsecant of log x. So we'll need to go to our derivative rule, and I guess I can get that in the shot as well. So u, the inner function inside of arcsecant, is going to be the natural log. But otherwise, we can apply this rule directly. Wherever we see a u, we're just going to write the natural log. So in the denominator, we'll get a natural log of x, and that needs to be inside of absolute values. And underneath here, we need to have a natural log squared, where there's a u squared. And minus 1. And up top, we get a 1. And then we need to multiply by the derivative of the natural log of x. What's this derivative, anyone? What's the derivative? Right, I think you said 1 over x, right? Yeah, that's correct. Okay, so let's just write that on the next line down here. So we have this first kind of messy function. And the whole thing gets multiplied by 1 over x, which came from the inner derivative. Okay, good. So that's how the rule works. Any questions over the derivative? Okay, so if there aren't any questions over the derivative, let's just go straight to an integral problem. So this one is the integral of dx over the square root of e to the 2x minus 4. So you might be wondering how this could possibly be related to the other rule. And we're going to have to work through, do a little bit of work to make it look like our new integral rule. So the first thing I want to do is a u substitution. Here I have e to the 2x in the denominator, and my u substitution is actually just going to be e to the x. And that way e to the 2x is u squared, because the exponent has been multiplied by 2. So if u is e to the x, then du is going to be equal to the derivative of e to the x, which is e to the x itself, times dx. And I also want to make a substitution for the constant, just like we had an a squared in this rule. I want to go ahead and think about what a should be. And since I have a 4 here, a is going to be 2. So let's see what we get from this. Well, before we get any further, you'll notice that there is not an e to the x here with the dx. So I'm going to have to rearrange this du equals e to the x dx to this. So dx is equal to du over e to the x, but remember e to the x is just u. So instead of writing it as e to the x, I'm going to write it as du over u. So dx becomes this, du over u. E to the 2x becomes u squared. And minus 4 becomes minus a squared. And once we make the substitution, we actually do have something in exactly the form that we need to use our new integral rule. The only thing that makes it look a little bit different is this du over u up top. Since we're dividing by u, I can move that down to the denominator. So just put it down here. And once we do that, we do have something that looks exactly like our new integral rule here. So we just have to apply 1 over a arcsecant of the absolute value of u over a. So a was 2, that means we get a 1/2 in the front, and then we get an arcsecant, and then the absolute value of u, e to the x, over a, 2. And then since this is an indefinite integral, we'll add a constant c. So this little trick might actually be the first time you've seen this trick of substituting in a u for e to the x when you have something that looks like this. So e to the x to a power can sometimes look like e to the something times x. And this is a helpful little substitution that might come in handy on all sorts of problems this semester. Any questions over that integral? Okay, so like always, if you do think of a question, go ahead and speak up. There's probably other people in the class that have the same question, but just don't want to ask it for some reason. And before we move on, I want to go ahead and give you the rest of our derivative rules. We had talked about arc sine, arc cosine, and arc secant. There are, of course, rules for all of the other inverse trig functions. We just don't have time to talk about them in class in too much detail. So for arc cotangent, that's the inverse of the cotangent function. We get a rule that's similar to the tangent rule. So we get a 1 over 1 plus u squared, but there's an extra minus sign in the front. And then for arc cosecant, we get a rule that's similar to arc secant, again with an extra minus sign in the front. But otherwise it looks the same. Still a 1 over the absolute value of u, and then a u squared minus 1. And the way I'm writing it, I need an inner derivative, a du dx. Let's see, and then arc cosine, I think I might have mentioned earlier, but I'm going to go ahead and just write it again. It's similar to arc sine, but with a minus sign in the front. So it's a 1 over the square root of 1 minus u squared. And then we need the inner derivative, du dx. Okay, so one thing I should mention before I move on is that I'm not going to give you new integral rules for these three functions. The reason why is that the only difference between these derivatives and the ones that we already learned is these minus signs. And we already know that when we're doing an integral, we're free to move constant multiples, like minus signs. This is like multiplying by -1. We can always move these outside of the integral to the front. So the integral rules that we already know for tangent, for arcsecant, and for arcsine work. You just have to move the minus sign to the front. So we don't need any new integral rules for those. So I'll pause there for just a second. Make sure you guys have enough time to write those down on your paper. And then we'll move on to one final example. Okay, so here's my example. I'm integrating dy over y squared plus 6y plus 10. So does this look anything like the rules that we've been talking about in the section? What do you think? Can we use one of our rules? Can you think back to another example? Anything? And it's all right if you say no, because that's what I would think looking at this. This doesn't look very much like the rules that we learned. So in order to use any of these rules, any of these or the other ones for integrals, we're going to have to do some rearranging. And what we're going to have to do for this one is complete the square, which is a technique that you might not have seen for a while. So I need to be sure to review how it works. So completing the square works like this. So often, I say often, but in math, sometimes you run across expressions like this: x squared plus bx plus c. So you're looking at a quadratic of some variety. But what you would want to do is actually somehow factor it, but you're not sure how. And completing the square is a technique in order to help do that. So what you're going to do is take this number here, the coefficient on the x term, and you're going to, well, let me write some of it down. You're going to divide it in 2 and square it, like this. But we don't want to alter the value of this. We don't want to change it. We want to get something that's equal. That's what I'm trying to say. So if I'm going to add this number, I also need to subtract it so that I don't change the value of what I started with. And then we need a plus c at the end. But we actually gained something, even though it looks a little messy, like we made things worse. But if we group this stuff together, this first bit, we're actually looking at a perfect square. This is actually just x plus b over 2 squared. So we factored part of the original expression, and the only thing that's left over is this constant. So it's going to look a little bad when I write it out, is this way. B over 2 squared plus c. But this is just a number. So we have something that's a perfect square minus a number. And that's useful, as we're going to see in this example. So I'm going to take this quadratic and complete the square in order to use one of my integral rules. So down here we have y squared plus 6y plus 10. So b, the coefficient on the x term, is going to be 6. Okay. So I'm going to take 6, divide it in 2, and square it. So 6 over 2 is 3. 3 squared is 9. So I'm going to add 9. But I also need to subtract it off so that I don't change the original value. And then I have to bring c along as well, so plus 10. Okay. And then we do the grouping. We group the first 3 terms together, y squared plus 6y plus 9. And this is something that you should recognize as a perfect square from your algebra days. This is actually just y plus 3 squared, right? And then the leftover stuff, that's just a couple numbers. Minus 9 plus 10, that's just plus 1. Does this look a little bit more like something that we could use our rules for? Well, maybe we haven't had enough practice for that to be the case yet, but if we go back to get it on camera. Our rule for tangent, we have du over a squared plus u squared, where a squared is just a number and u squared is a function. So down here, we do have that constant, 1 is equal to 1 squared, and then a function squared. So this is actually going to be a arctangent. If we do a u substitution, see, there's a little bit of room down here. If we do a u substitution with u equals y plus 3, and du is the derivative of that guy, which is just 1 times dy. So do your substitution. This one is relatively easy since we've done the hard work of completing the square. We get a du in place of dy, and then a u squared plus 1, or plus 1 squared if you prefer. Okay. So draw in a little line there. To separate this out from our earlier work. So this is going to be an arc tangent. A is equal to 1, u is y plus 3. So does anyone know what the answer would be? No one's volunteering. So it's arctangent or tangent inverse of u over a, or u over 1. So it's just arctangent of y plus 3 plus a constant, since we're doing an indefinite integral. So any questions here at the end of class? Okay, so we'll stop there.